When an object is acted on only by conservative forces, the mechanical energy may be transferred between kinetic and potential energies, but the total mechanical energy, that is the sum of kinetic plus potential, is a conserved quantity. Consider the trajectory of this snowboarder. Initially, he has only kinetic energy, 1/2 mv0 squared. Note that this initial velocity, v0, results from the vector sum of the horizontal and vertical components of velocity, v0x and v0y. Partway through his jump, he has a combination of kinetic energy, 1/2 mv squared, and potential energy, mgy. By the Pythagorean theorem, v squared equals vx squared plus vy squared. Although the x component of velocity remains fixed, since there is no horizontal force, the y component is reduced by the downward acceleration due to gravity. At the peak of his trajectory, he maintains some kinetic energy because of his horizontal velocity, but has maximized his potential energy. During the downward descent, he trades potential energy of height for kinetic energy with more speed as the y component of velocity increases in magnitude again. Finally, as he returns to his original height, he has lost all potential energy and has recovered his kinetic energy. Throughout this flight, his total mechanical energy has remained the same. A swinging pendulum can illustrate the same energy conservation ideas. When displaced far to the left and released, the pendulum has a potential energy of mgh due to its height h above the equilibrium position. As the pendulum swings downward, it picks up both horizontal and vertical components of velocity while it loses height. Once again, the square of the speed is equal to the sum of vx squared plus vy squared. At the equilibrium position, that is the bottom of the swing, the potential energy has all been transferred to kinetic energy, 1/2 mv squared. On the upward swing, kinetic energy is transferred back into potential energy. Finally, at the far right of the swing, 1/2 of a complete cycle, the potential energy is once again maximized, and all kinetic energy is lost. Yet throughout, the total energy has remained constant. If the kinetic energy of the pendulum were to be plotted as a function of time, one would find that at the far left of the swing, the kinetic energy is 0 for the brief moment of turnaround. The kinetic energy is maximized when the pendulum passes through the bottom of its swing, and finally the kinetic energy is back to 0 when the pendulum bob turns around at the right extreme. A plot of potential energy shows just the opposite, with the height, which is proportional to potential energy, maximum at the two extremes of the motion. The total energy, which is the sum of kinetic plus potential, should remain constant, however, throughout the entire swing. Begin the experiment by hanging a pendulum in front of the white poster board screen. Here we've put a white rubber band around the middle of the black pendulum bob for easy location of the center of the bob in subsequent video clips. Place a webcam on a jack stand at one end of the table. Notice that we lay a meter stick on the table under the swinging pendulum so our video can be scaled. Once you've captured the video using the webcam and converted the file to a .mov type file, open the program called Video Point. Drag the slider along the bottom until the pendulum is at an extreme of its motion. Carefully center your cursor crosshairs on the middle of the bob and left click. The video will automatically advance to the next frame. Clicking on the icon with red trajectory marks causes a red dot to be placed on the video where you previously clicked as the video advances to the next frame. Continue in this way until the bob has swept across your line of sight and a path of red dots outlines the motion. Your video points must now be scaled to the meter stick you conveniently laid at the base of the pendulum. Click on the icon at left that looks like a ruler and indicate that the object you are using to scale is exactly 1 meter in length. Then use your cursor to indicate the left end of the meter stick, followed by the right end of the meter stick. Open a data table window using the appropriate icon to the left. The table displays the frame number, the time, and the X and Y positions in meters. Note that most of the frames are blank, since you did not click on them. Highlight the data you collected by dragging over the frame numbers and copy the data for transfer to the plotting program called Graphical Analysis. Using Graphical Analysis, relabel the first two columns to represent time and X position values. Use the Data menu choice to create a new manual column called Y. Paste the data you had copied from VideoPoint into these empty cells. We will now create a series of new calculated columns using graphical analysis like a spreadsheet to generate kinetic, potential, and total energies. First, we need X and Y components of velocity. Since velocity is the time derivative of position, create a new calculated column defined as the derivative of the X column with respect to the time column. Create a similar column for the Y component of velocity. Now create a column representing the kinetic energy per unit mass. We use the energy per unit mass since we have not measured the mass of the pendulum bob and don't need to. The kinetic energy per unit mass will be 1/2 v squared, or 0.5 times the quantity Vx squared plus Vy squared. We will compute the potential energy per unit mass relative to the low point in the pendulum swing. This equilibrium height will be called y0. y0 is easily picked out of the y column of the table and is used as a numerical value in the calculation of the potential energy column. The definition of the potential energy per unit mass will then be 9.8 times the quantity y minus y0. Finally, the total mechanical energy per unit mass is the sum of the kinetic and potential energy contributions. Here's a plot of our kinetic energy per unit mass. The undesirable spike to the left of center is due to small errors in locating the center of the bob. Any errors in position become magnified when the velocity is computed. Since the kinetic energy depends on the square velocity, the small error becomes even more exaggerated. Here we have added a plot of potential energy as well. Finally, we plot the total energy, which is somewhat constant, with some variation due to positioning errors. You can highlight the total energy data and perform the statistical computations readily done through graphical analysis to determine the ratio of standard deviation to mean energy. This experiment may be repeated for a tossed ball. Starting with the frame where the ball is completely released, track its motion until it hits the table. Here's a plot of kinetic potential and at the top, the total energy.